So this question says classify all the point of inflection of y equals 2 minus x cubed. The first thing, of course, is you differentiate, you get minus 3x squared, right? At stationary point, again, a stationary point and a turning point have some differences. Stationary point could be turning point and it could be point of inflection. Okay? Now, at stationary point, dy by dx is equal to 0. So which means, and the only solution is x is equal to 0. Now when x is equal to 0, y will be 2 minus 0 cubed, which is 2. So the point we're talking about is 0, 2. It's a stationary point. As a matter of fact, that is the only one we can see here. It's a stationary point. But we need to classify this. So we find the second derivative. d2y dx squared is equal to negative 6x. Okay? This one method you could use is to observe the rate of change about this stationary point. The rate of change of the gradient. How does the gradient change about this point? Anything below here, like negative 1, will give you positive. Anything above will give you what? Negative. It means there was an increasing gradient, right? You're getting a positive gradient. Then what happens again? Wait. Yeah. It means, is this my second derivative? Yes, that tells us the behavior of the first derivative. So this sign diagram is correct, yes? So it means the gradient, there's a change of negative to positive at this point. Are you getting me? So the gradient, so there's a change in the curve. That's the implication of this. When do you get positive as a gradient? When you have something like this. Is that not? When do you get negative? I mean the rate of change of gradient. It's coming from negative gradient, then it's going to positive gradient. So there's a change, there's a positive increase. There's an increase in the gradient, sort of. But when you have something like this, the gradient was positive. Then as it moves forward, the gradient becomes negative. There's a decrease. So for this one, the d2y dx squared will be what? It's coming from negative gradient to positive gradient will be greater than 0. It means there's a positive change because it's increasing from negative to positive, right? But from here, it means the second derivative, there's a negative change in the rate of change. Are you getting my point? So if you combine these two, it's like having something like this, then you change your mind. So this is the point of inflection we're talking about, but it's a non-stationary point of inflection. Do you understand? Because at this point, the gradient is not necessarily 0. Do you understand? But in this case, that's not, I'm not saying this is the situation. I'm saying there's a change in the shape of the curve. So anywhere there's a change in the shape of the curve, definitely you have a stationary point there. So it's possible your curve is like this also. And then, so there's a change somewhere here. Are you getting me now? There's a change here. Because it's coming this way, then, okay, the shape changes like that. But here, you have a stationary point of inflection. So if you have to find this whole calculation also, there will be a change as well in the shape of the curve. So what this picture is telling you is that there's a change in the shape of the curve. And whenever you have such a situation, you know you are dealing with a point of inflection. But if your gradient at that point is equal to 0, then you have a stationary point of inflection. If your gradient at that point is non-zero, then you have a non-stationary point of inflection. So the non-stationary point of inflection is this form. This is the shape of the stationary point of inflection. Does that make sense now? So here, so by this implies that there is a change in the shape. Or we can say curvature. Remember, that's the key. Is that the shape of the curve or curvature? From what to what? Positive means it's going this way. Negative means going. So from what to what is that? From concave upward to concave down. Understand? Okay? Hence, 0, 2 is a point of inflection. But remember the question says classify all the points of inflection, right? So they acknowledge already that the point we obtained is a point of inflection. But what do they mean by classify it? Anyone? Stationary? Is it stationary or non-stationary? So at this point, what happens to the gradient? That's how you know. Okay? What happens to the gradient? The gradient will be 0. So this point is not just a point of inflection. As a matter of fact, it's a what? A stationary point of inflection. Okay? So definitely, you have something like this. Something like that, where this is the point in question. Understand? So if you plot that, if anybody can check on their calculator or put on decimals, let's see what happened to that point 0, 2. Are you there yet? Did we get that? I'm not sure if it's facing the other direction. I just sketched something. Is it facing this direction? Okay, that's it. And that's like the y-intercept, isn't it? That's the y-intercept. So you just need to be able to distinguish between the stationary and the non-stationary point of inflection, please. Okay, so let's look at number 3. Find and classify all the points of inflection. So another problem. Of course, to differentiate, you need to write this function properly without fraction, right? Then we can find the first derivative. dy dx is 4x plus 12x cubed. Am I right about that? So 4x plus 12 divided by x cubed. Okay? At stationary point, we don't know if the stationary point is a turning point or a point of inflection. A stationary point, so I'm calling it the general name. dy by dx is equal to 0. So if 4x plus that is equal to 0, it implies that 4x is equal to negative 12 over x cubed, yes? Which implies that 4x to the power 4, right? Because negative 12. Am I right about this? Or have I committed a blunder? Yes?
I started with second derivative.
Yeah, wouldn't it make more sense to start with the second derivative? Because you have to find the point of inflection. I mean, we don't know if the stationary point is a point of inflection.
Definitely. No, if you go on like this, it just tells you something. That there's no turning point, right? Because you are supposed to get a point that where it turns. clearly we can't get that point out of here. I can see why you have to go to the second derivative now. Anyway, we know that at this point you should get 0, right? But we can't pinpoint what the point is, right? So let's go to the second derivative.
I guess you can keep it, then you can just use that to say there's no stationary. Like the points of inflection are not stationary.
So it's going to be a non-stationary point of inflection, sort of. Okay. So if we say this, if x to the power 4 is equal to -3, which has no solution, right? Which has no solution. Okay? Which has no solution. And the implication of this would be what? There is no, right? Stationary point. So if you eventually get a point of inflection, it has to be non-stationary. Okay, there is no stationary point. There is no stationary point. There is this no. I believe I've mentioned that before. Okay, thanks for that. d2y dx, I was going to erase everything again. So this will be 4. This will be 36. No. -36 minus 4. I'm running against the clock. That's why I'm so fast, sorry. So you get 4 minus 36 divided by x to the power 4. If you find error later, please fix it and just let me know. I probably made something out. Now, so if you want to know, at that point of inflection, of course, your second derivative should be 0. Yes? So, when that is equal to 0, it implies 4x to the power 4 is equal to 36. Am I right about that? X to the power 4 is equal to 9, which means x squared is equal to 3, which means x is plus or minus root 3. Okay? So we can put this back to get the corresponding y, but let's sort the x first. Okay, so when x is 3, we can draw, so we have two possibilities here. Minus root 3 and plus root 3. Okay? And we know that it doesn't exist when x is equal to 0, right? So use broken line there. That's where it does not touch anything on y. So we need to justify that, because if that happens, there might be some behavior on this part, there might be some behavior on this part. That's why you need to take note of that point. Now, this is 1 point something. So 1 is a point here. This is minus 1 point something. Minus 1 is a point here. Minus 2 is a point here. Plus 2 is a point here. So we can use those points to check for the signs. So if we check 2, for example, if you put it in here, what is this? 36 over 16, right? That is 2 point something, right? And that would be positive. So this is positive. Check with 1. Is that negative? Check with minus 1. Same. Because that would be negative, sorry. Right? Then check with plus 2. It's going to be the same as this. Agreed? So, at these 2 points, there's a change in the shape of the curve. Right? So it was positive gradient, there's a negative change, this is a positive change. Hello? So there is a change in this, just like this one. Okay, there's a change in the shape of the curve. It was concave up to down. Okay, concave up to down, because at first it was like this, going from negative gradient to positive gradient, then it changed back from negative gradient to positive gradient. So you can see that, oh, there's a concave up, then down, here. This is from concave down, then up again. Is that not? So these 2 points are our point of inflection, and from the other ones, we can see that they are non-stationary point of inflection. Does this make sense? So, but what are the corresponding y at these 2 points? What are the corresponding y? Or did they just say the values of x? No, it said classify the point. So when you are talking about point, it's not just x. You have to know the corresponding y. So at x is equal to negative root 3, y is equal to what? What is 6 times? This will be 2 times 3. Minus 6 divided by 3, right? So 6 minus that. Am I right? So please tell me if I'm wrong, please. I might have said rubbish. So this is also 2 times 3. It looks like it's the same. Okay? So the point here is, we can just say therefore, minus root 3, 4, and root 3, 4 are what? Non-stationary point of inflection. Can you check online what the shape looks like? This class ends at 12:30, right?
Yeah.
So we have about
但是会再变更。
Is it? Okay. So now, so there is no stationary, there's no turning point basically, right? There's no turning point basically. Okay, so the third one, quickly, number 7. You can look at number 5 yourself. It's talking about finding all the point of inflection of arctan x minus 1 over 2. I want to leave that to you to please practice, all right? But let's look at the fourth one here. Consider the logistic function. That is probably going to be the last one because of our time. But before then, can you go to question 10 and tell me if you know how to begin with that? The first one says determine whether f is even, odd, or neither odd nor even. Karen, how would you begin this problem? You start with f of negative x, okay? And you can show if it is, if you are able to get minus f of x, you are good. If you are able to if you are not able to get it, then it is neither, all right? If you have minus, yes. If it is the same as f of x, it is even. But if it doesn't show even or odd, you say it is neither even nor odd. Okay, you can investigate that, and I would like to have some feedback by Monday. You don't have to submit, just tell me you've tried it, okay? Then, because this is a past question, so if you see any marks allocation, I pick it from IB past question. Then show that something is equal to 0. I believe you can always solve that with your knowledge of product rule and every other thing. And with that, I briefly explain why or why not f has a point of inflection at 0, 1. Does it have or does it not have, and why? So you just have to go through with this calculation. The same thing we did for algebraic function, you do the same for trigonometric function. Okay? So I'll leave that to you, please. I won't be going back to point of inflection as a topic again in class because of our time. All right, let's go to question 7. Question 7, consider the logistic function f of t c over 1 plus a exponential minus bt, where t is greater than or equal to 0, which means this sign is always negative, except when b is minus. All right, where a, b, and c are that constant a. Find the y-intercept. Y-intercept is when what? When t is equal to 0. This time around, they are not dealing with x, so you have to be very careful. So when t is equal to 0, f of 0 will be c divided by 1 plus a times exponential 0. Agreed? So a times exponential, that would be 1 plus a. So that's the y-intercept. Okay? Or 0, comma, all those stuff you can see. B, prove that y is equal to c is its y is the horizontal asymptote. Horizontal asymptote is when what happens? That is when x tends to what? Remember, if you have a curve, this is what we call the horizontal asymptote, right? When x tends to infinity. That's the easiest way to get it. This is not like the rational function where you could do what we did then, all right? But now you have learned limit, okay? So just say as x tends to infinity, f of t tends to c divided by 1 plus a exponential, it's like negative infinity, sort of.
As he tends to infinity, not x.
Oh, you see? I didn't get enough sleep too. Understand? So it sounds like this. Of course, infinity is not a number. Do you understand that? So, okay, let's say as t tends to infinity, exponential minus bt tends to 0. Do you agree? Do you agree? So this is a better way to write. So f of t will tends to, is that understood? So which will be c divided by 1, which is equal to c. You can see? Therefore, y is equal to c. I think this is capital C actually. I'm writing it like it's a small letter. So let's be mindful of the notation in the problem. Alright? Is the horizontal asymptote. So just use your knowledge of limits. Remember, when you have positive, that is when it diverges. But when you have negative, it converges. Because it's going to be exponential negative x, right? 1 over exponential x. So when this becomes big, everything becomes smaller. That's what we are saying. I hope we can see that part. Oh, sorry. Just, okay. So when c tends to infinity, so this is the horizontal asymptote. Okay? That's simple and straightforward. C. Prove that if a is greater than 1, there is a point of inflection with y coordinate that. Okay, let's see. To even talk about anything, you have to differentiate first. So which is going to be, I don't know how easy that will be. Let's try. Hopefully we'll. Don't listen to that. 2 minutes to the end.
Negative to the power of negative 1.
What?
The
A plus 1 plus 1.
Oh my god, that makes it more complicated. So negative c, right?
Yes.
Everything will be negative 2. So 1 plus a exponential negative bt times what? 0 plus negative ab, right? Exponential negative bt. Karen, understand? For exponential for chain rule, you multiply by derivative of the bracket. The bracket is an exponential function, term by term. You differentiate this 0. You differentiate the exponential function with a power. You copy and paste the function. You multiply by derivative of the power of the function. There are so many copy and paste there. So that becomes ABC, correct? So A, B, C. I think everything would be divided. Exponential. Oh my God. BT.
Yes.
Okay, we can use BT here. And here also, 1 plus a exponential negative bt all squared. Something like this. Okay? Now, if you are looking for point of inflection, if you try to equate to 0, there will be no point, right? Just like question 2. Or is there? If you equate to 0, oh, there might be. Because actually we could have left this here. Are you getting my point? We could leave this here. Let's see. You leave this here, exponential negative bt.
But it can't be 0.
Oh, it can't be 0 because exponential, unless, and we don't, and those constants are positive. So this cannot be 0 automatically. Alright, because these constants are positive, so they are non-zero. Exponential is never 0. So there's no way you will say this fraction is 0 when the numerator cannot be 0. So it can't be 0. So don't waste our time equating it to 0. Just take the second derivative. Let's just write it back in a simpler way. That's a product rule. Oh my God. Exponential negative bt. I'm going to abandon this question for you to do. This is where I leave you to your problem.
Oh.
Well, I didn't mean to be a bad friend, okay? All right, so product rule, let's see. 1 minute, I can still delay it for 1 minute. So the first part, leave that, copy and paste the first one, ABC exponential negative BT, and differentiate the other one. To differentiate that, we get what? Minus 2, the bracket will be minus 3, then we multiply by negative AB exponential minus BT. Yes? So the constant bracket will be that. Am I right?
Yeah.
Then plus, this is leave this constant and differentiate this, right? Then leave this constant and differentiate this. So when you differentiate this, you get A, B, C, followed by minus B, right? Exponential minus BT, okay? Then you just copy the other one. 1 plus A exponential negative BT raised to the power minus 2. So that's it, right? Then we have to be able to simplify. Can I ask you to try to simplify this? See if you can equate it to 0. Maybe something can happen. Okay? So just follow through with this. After the second derivative, check what happens when it is equal to 0. Alright? See if you can get some behavior. Then if I also find some time to solve it, I can send you a solution. But if somebody gets it first, Lillian is doing something. If you get it, please send to the group also. By the way, I broke my phone yesterday, so I won't be available today. If anybody's trying to reach me, I'll try to log on my WeChat on my computer. Hopefully, I can still be reachable. But if my system shut down for whatever reason, I'll be off till Monday morning.
Okay.
From today. I was playing volleyball with the P6 babies yesterday.
Oh.
And I had the phone inside the hoodie, your hoodie. So I forgot, I should have put it here. So it's more protected. So I should have then I was, just playing, trying to block somebody, I was just being wicked to the girl. She wanted to, that short, the basketball, I'm like, okay, I'm taller than you, I'm gonna block it. So we're just having fun, and the next thing, we just, boom. I'm like, wait, why are they screaming? They were screaming on my behalf. And when I saw it, I'm like, no! Just 1 month to change my phone, this guy can't just wait.
No.
Then I checked Apple Store yesterday. I can't even book until 6 a.m. to book for iPhone 12.
Oh my god.
I don't want 12, I want Pro Max.
Wow.
So I don't have to buy for the next 2 3 years.
Yeah.
But somebody said it's going to be a big phone, but I think I can handle it. Because the review shows that it has the best of the things, right? So at least I can show it to clearances and say my phone is better than theirs.
It's really big.
Really big, right? Hopefully I like it. I once used Nokia Lumia. It's a very big phone.